In Azure, the most common service to use to monitor your system is Application Insights, or App Insights. App Insights has a tremendous number of features that can help you to determine the overall health of your system. For example, with App Insights, you can actually explore, monitor, and somewhat manage the overall performance of your application or service. And how does it do that? Well, each operation that your service performs is captured by App Insights and stored for a period of time, usually 90 days. The details of each of these operations can then be analyzed. Of course, this can include looking for issues or searching for specific operations and whether they were performed in an expected order. But it can also include timing or resource consumption. And that information can be analyzed to determine how your system is performing over time or under certain conditions. Now, this is all done through telemetry monitoring of your application or service, and most Azure services automatically emit telemetry that can be consumed by App Insights, but you can also generate your own telemetry too. So, how does this pertain to data science or models that you generate through Azure ML Studio? How can we make use of a tool like App Insights when we generate models in Azure? Well, the first thing we need to do is provision an instance of App Insights in Azure and associate it to your ML workspace. When you provision an instance of the Azure ML workspace, you're asked to create or reference a set of other Azure resources, and one of those resources is App Insights. Now, during the creation process, you can reference your own existing App Insights resource, or you can choose to create a new one specifically for your ML workspace. What that means is that you'll always have an App Insights instance associated with your ML workspace. However, that doesn't mean that your models will automatically send information to App Insights. In actuality, when you create a web endpoint for your model, you can choose to send the model's telemetry to App Insights. Of course, you can choose not to, but generally you want to do it, if for no other reason than you can capture any errors that your model encounters when the users submit their own data. So what's the actual step-by-step process of associating an ML workspace with an instance of App Insights? Well, like I said, the association of App Insights to an ML workspace is configured during the provisioning process for an ML workspace. During the provisioning process, you're asked to select an existing App Insights resource to attach to the ML workspace. Sometimes businesses have a single central App Insights deployment for all their services. So in that case, it's a good idea to attach a new ML workspace to that central App Insights deployment. But you don't have to do that. If you don't select an existing App Insights instance, then a new one's going to be created for you. And that new App Insights instance will then be specifically and exclusively associated to your ML workspace. And what this means is that an ML workspace will always have an App Insights instance associated with it. Now, once an App Insights instance has been attached to an ML workspace instance, there's certainly going to be instances where we want to find that App Insights deployment so that we can explore the data that it's captured. Now, besides just knowing the name of the App Insights resource and where it's stored, there's a couple of ways of finding that App Insights resource. The first, and easiest, is to use the ML Workspace's overview page in the Azure portal. The ML Workspace includes links to all sorts of related Azure resources. One of the links will be the App Insights instance that has been associated with the ML Workspace. Now, the reason the Azure portal is nice is because the App Insights instance reference is rendered as a link. So you can simply click on the link and find yourself in the App Insights instance ready to perform whatever analysis you want. But not every situation allows for point and click. There is a code option. If you find yourself in a code environment, you can get a reference to your ML workspace and then call the getDetails method. You'll always have the workspace object because you need that to interact with models anyways. Now with the getDetails method, you can get the various references associated with the workspace and then use that to access other resources, including App Insights, using the appropriate objects and packages. Good. So now we know we have an App Insights associated with our ML workspace. But how do we go about capturing and analyzing telemetry? Well, first of all, App Insights automatically captures any data that's written to the standard output. It can also capture error logs in the same way. Of course, not everything outputs to those outputs, so when you create a model endpoint, you need to specifically associate that endpoint to App Insights so that it'll begin transmitting data to those outputs. Now, once you have the data being output, you can view that data using queries. These queries can be written in code, of course, but the App Insights UI provides a much nicer interface for querying and reading whatever data you've captured. Now, logging to App Insights isn't that hard either. All you have to do is output your telemetry to the standard output, and in Python, that's as simple as using the print statement to log your information. There certainly are App Insights specific methods that you can call if you have the right SDKs installed, but you don't have to go that far unless you have specific needs to capture data a certain way. Now, once the data is written to standard out, that data is written to App Insights. Now, it's important to note that any details in your log are actually captured as a custom dimension to the telemetry entry in App Insights. And App Insights will actually capture the telemetry messages as standard out. That's where the specific App Insights packages might be useful, but custom dimensions are perfectly fine as long as you do so consistently and use the right queries. Alright, but just how do we query App Insights? Well, as I said earlier, the best way is to use the Log Analytics query interface in the App Insights user interface. The Log Analytics query interface allows you to use a syntax very similar to SQL to query your telemetry data. There's tons of ways you can query that data. You can query for traces, exceptions, metrics, and more, and you can even join various aspects of your telemetry too. And to make your life easier, App Insights also includes a whole host of built-in queries that are very common. So you don't have to invent your own queries, but you do have all the power in the world to do so if you want to. Now, as I mentioned, much of the information that's collected from models is embedded in what's called custom dimensions. With App Insights, you can actually inspect individual fields like that and extract fields and data from them. To put that into context, the custom dimensions field is a single field that contains JSON, and App Insights queries can extract fields from that JSON object and query even more deeply into those fields. In this demo, we're going to train and deploy a classification model and then monitor that model. We'll do that by deploying the model with Azure ML Studio's Notebooks feature and writing some Python code. Now, before we get started, this demo assumes that you've already provisioned an instance of Azure ML and that you have access to the Azure ML Studio. If you don't, you'll need to provision one and set up the needed compute. Now let's get started. The first thing we need to do is head over to the Azure ML Studio in our browser. Now to run this demo, we're actually going to execute code from the Azure ML SDK. Now to run code in ML Studio, we need to use the Notebooks feature. So let's go ahead and click on Notebooks in the left-hand menu. Now what we're going to do in this demo is we're actually going to use a sample from Microsoft to run through the steps of creating a model to monitor. To use the sample, we first need to clone a repo from Microsoft. So in the File List toolbar, click on the Terminal button. Now this will load up a terminal that we can use to issue commands in. So let's type a git clone command. Let's type git space clone space https://github.com/Microsoft Learning, all one word, /mslearn-dp100. Now what this command does is clone the DP-100 sample repo from Microsoft into our notebook files. So let's execute this command and wait for it to complete. Now in the file list, let's click on the Refresh toolbar button above the file list. Now we can see the MSLearn DP-100 folder. Now we can finally access the sample. So let's open that folder and find the 16 Monitor a Model file and then click on it. Now as you can see, Microsoft has a lot of information in here that explains what each particular step is doing and what it means. It's definitely worth your time to review this in detail, but in the interest of time, we'll go over this fairly quickly. So let's start by scrolling down to the first code cell. Now this code cell connects our compute instance to the ML workspace and gets us authenticated. So let's run this code by clicking on the play button to the left of the code block. Now if the output asks you to authenticate, go ahead and follow the instructions to do that. Now let's scroll down to the next code cell. Now this code cell does a bunch of things, so let's go over it. First, we're creating and preparing the dataset that we'll need for our model. So on line 13, we're uploading some diabetes data to the default data store. And on line 20, we're creating a dataset based on the data that we uploaded. Then on line 25, we're registering that dataset so that it can be used by various models. Now once the dataset is registered, we move on to experiments. So on line 34, we create an experiment, and on line 35, we create a run. Then on lines 40 to 46, we load our dataset into a few variables so that we can define the features and labels. We also split the data into a training and testing dataset. On line 50, we train the model using a decision tree classifier. Then on lines 53 to 62, we log the accuracy and the AUC model metrics. And on lines 65 to 67, we save the trained model and upload it. And finally, on line 74, we register the model. So let's run this code block and get this all going. Our dataset is registered, our model is trained, and our model is registered. Now let's scroll down to the next code cell. Now in this code cell, we're preparing to deploy our model as a web service. So the first thing we have to do is create a run location. Basically, this code cell creates a folder. So let's run this code cell to create that folder. Now let's scroll down to the next code cell. Now in this code cell, we're creating a script file that will live in the folder we just created. On lines 11 and 12, you can see that a model is loaded from the run location. Then on line 17, you can see that this script loads a given dataset. And then on line 20, the model is executed against that dataset to get some predictions. Now the rest of the code is about returning the results. Okay, so let's run this code to create that file. The file has been created. Now let's scroll down to the next code cell. Now in this code cell, we're creating an environment. When you run a script-based experiment, you need an environment to run it in. And this script will have dependencies so the environment can load those dependencies. Let's run this code and get that set up. The environment has been prepared. Now we can scroll down to the next code cell. Now in this code cell, we're finally deploying our model as a web service. What's important here is that an inference cluster is created along the way. So this can actually take some time to create. Now let's run this code, and I'll fast forward to the end so that you don't have to wait. Now with our model deployed as a web service, we can get to work using and monitoring it. Now when it comes to monitoring, there's lots of ways you can do that. As we talked about earlier in the course, one of the most common ways is to use the app insights associated with our ML workspace. So let's scroll down to the next code cell. In this code cell, we're enabling App Insights for our model. App Insights is extremely useful. It can monitor your model, determine performance issues, and log whatever needs to be logged. It can even include some intelligence on where it can detect abnormal behavior and let you know if it finds any. Anyway, let's run this code and enable App Insights. Now let's scroll down to the next code cell. In this code cell, we're actually going to get the endpoint for our web service. Let's run this code and see what it is. Now that's an easy endpoint to remember, isn't it? Well, not really. But then again, this is a globally unique URL, and it isn't generally important to end users anyways. Anyway, let's scroll down to the next code cell. Now that we have the endpoint, we can start making requests against it. We trained a model to predict whether patients were diabetic. In this code cell, we're going to call our model with some patient data and have that model tell us its prediction as to whether the patients are diabetic or not. On line 5, you can see that we create some data. It's not very clean, but rest assured that it maps to the needed data. On line 9, we convert that data to JSON in an object called data. And on line 15, we call our endpoint and pass in that data. The result of that call is then put into a variable called predictions. The rest of the code outputs the data to the screen. So let's run this code and see what we get. Our model took the input data and determined whether each patient was diabetic or not. So you can see that the first patient was classified as diabetic, and the second patient was classified as not diabetic. Okay, but what about the monitoring? Well, remember how we connected our endpoint to App Insights? Well, all the monitoring is being done in that service. So we can see the monitoring results there. So let's scroll down a bit to the text after this code cell. Now notice in item 4 that there's a query. So let's copy that text to the clipboard. Now in another tab, let's head over to the Azure portal. And good, now let's head over to our machine learning workspace. Now mine is called SBDemo16, so I'll search for that in the top search bar and then click on the results. Now in the overview screen, notice that there's an Application Insights item in the top section. So let's click on that link. Now at the top of the screen, let's click on the Logs toolbar button. And we'll close any of the helpful pop-ups. Now in the query section, let's paste the query that we copied. Now before we execute this, let's remove the condition about the message being a standard out. I mean, after all, it's not always going to be a standard out. It could be an error. Now let's click the Run button in the toolbar to get the results. So there's all the logs for the model execution that we just performed against the web service. Now I won't bother going into all the details of the actual telemetry here, but this shows you how you can find your telemetry and inspect it in case of any issues or other analysis needs. Anyway, there you have it. With a simple configuration of a model, we can enable monitoring like App Insights and review information about our model whenever we need to. With App Insights, you can configure various thresholds, alerting, and even monitor things like performance so that you can make improvements on your model. In this demo, we're going to use a Microsoft sample to create a data drift monitor. We'll create a couple of data sets and then create the drift monitor to watch those data sets over time. So let's get to it. First, we need to head over to our Azure ML Studio instance in our browser. Now, as I said, we're going to run through a Microsoft sample related to the DP-100 exam to create a data drift monitor. In our last demo, we cloned a Git repo that already included that sample file. So let's head over there now. Let's click on the Notebooks feature in the left-hand menu. Now let's open the MS Learn DP-100 folder and click on the 17 Monitor Data Drift file. Now this file includes lots of good information from Microsoft on just what exactly is going on with each of the code cells and why. You should definitely spend some time and review this in detail. However, in the interest of time, we're going to go over this fairly quickly, but I'll still explain what we're doing with each code block. Now let's start by scrolling down to the first code cell. Now, in this code cell, we're verifying that the Azure ML SDK data drift package is installed. That package is going to be needed to execute the code in this notebook. So let's go ahead and run this code block to make sure we're good. The data drift package is installed, so we're good to go. Now, if for some reason your system doesn't have the package installed, simply change the command from show to install and run this code cell again. Now let's scroll down to the next code cell. Now in this cell, we're connecting our compute instance to our ML workspace, and this just makes sure we're connected and authenticated. So let's go ahead and run the code cell. Good, we're connected. Now if the output asks you to authenticate, go ahead and follow the instructions to do so. Alright, now let's head down to the next code snippet. Now, in order to monitor data drift, you need data to monitor. More than that, you need a baseline to know that drift is even happening. Obviously, when you train your model, you'll be using a training dataset. That dataset is generally the one that you use as your baseline dataset. So what this code cell is doing is it's creating a dataset from a set of predefined CSV files about diabetes patients. On line 13, we create the dataset, and on line 14, we register it. So let's go ahead and run this code so that we can create our baseline dataset. Now let's scroll down to the next code snippet. Now over time, you'll continue to train your model, and to do that, you'll collect all kinds of new data. Ideally, that data is, to coin a lyric from Daft Punk, harder, better, faster, stronger. Anyway, as we collect this new data, it'll start to deviate from the original training dataset. That deviation is what we call data drift. And what we're going to do in this code cell is we're going to create a target dataset. When we determine what sort of drift we have, we're going to do that by comparing the baseline with the target. Anyway, so what this code cell is doing is loading one of the original diabetes files that we used to create the baseline, and you can see that on line 7. And then augmenting the data slightly, and you can see that on lines 19 to 21. Then we're creating some new CSV files on line 24 to 26, and on lines 29 to 42, we're uploading the data, creating the target dataset, and registering the target dataset. So let's run this code and create our new dataset. We now have our datasets. So we can create our drift monitor. In fact, let's scroll down to the next code snippet. In order to use a drift monitor, you need to have a compute cluster. This code cell connects to an existing compute cluster or creates a new one. On line 4 is the name of your compute cluster. So I'm going to update this code to change that value to the name of my compute cluster. I called mine sbdemo16cc. Now let's scroll down to the next code cell. In this code cell, we're finally going to create our data drift monitor. Let's go over this code and see what the important bits are. On line 1, we import the data drift detector package. This is the package that we can use to actually create a data drift monitor. On line 4, we configure the specific features of our dataset that we want to monitor for drift, and that's important. You may not really care about the drift in various other features. In diabetes monitoring, pregnancies, age, and BMI play a significant role in figuring out if a patient is diabetic. So those are the features that we really want to pay close attention to. Anyway, on line 7, we create the monitor. And notice that we reference the baseline dataset and the target dataset. Those are the two datasets that we want to watch for drift. On line 8, we reference our compute cluster. And on line 9, we configure how often we want to watch our datasets for drift. In this case, we're going to check weekly. On line 10, we specify the features to watch. And on line 11, we indicate what our threshold is. If there are deviations beyond this threshold, that's when we want to know. Otherwise, we don't really see it as drift. Anyway, let's go ahead and run this code so that we can create our monitor. Our monitor is created. Now, as it happens, our two datasets were created at the same time, and this demo would take a long time if we waited for a week to see the results. So what we're going to do next is we're going to look backwards in time. So let's scroll down to the next code block. Our two datasets actually include data for over the last 6 weeks. So what we're going to do here is we're going to backfill the monitor. We're going to specifically tell the monitor to go review the already existing data over the past 6 weeks. And you can see that happening on line 3. Then we execute the backfill action on line 6. So let's run this code. Now this code might take some time to execute because it's starting up the cluster and running the backfill. So I'm going to fast forward to when this is done. So the backfill is complete. Now let's scroll down to the next and last code cell. In this code cell, we're actually going to look at the drift metrics produced by our backfill run. So let's execute the code and see what we get. So let's review what the output is telling us. First, we see the date range of the data fill analysis. Then we see the frequency of the analysis is weekly, just as we configured earlier. Then we see the data drift percentages. In the days from start field, we can see that we had 6 weeks of data to analyze, just as we configured. In the drift percentage field, we can see that our drift increases every week. In other words, we can see that our target dataset drifts further and further away from our baseline with each passing week. And remember, that drift analysis is being done on just a few of our dataset features. The drift could potentially be worse or better if we include other features too. And so there you have it. In this demo, we successfully created 2 datasets, a baseline and a target. And then we created a data drift monitor and asked it to go backwards in time to analyze the last 6 weeks of data. Since we created our target dataset by purposefully augmenting the original baseline dataset, we naturally were able to see a continuously increasing data drift between the 2 datasets as each week was analyzed. In this demo, we're going to explore data drift monitor visualizations using Azure ML Studio. To do that, we're going to piggyback off our last demo where we created a data drift monitor. So let's get started. Let's open our ML Studio instance in our browser. Now in our last demo, we created a baseline dataset that included a bunch of data about patients that may or may not have diabetes. We then created a target dataset based on an augmented version of the baseline dataset. Specifically, we took the pregnancies, age, and BMI features and adjusted them slightly for 6 weeks worth of data. We then created a data drift monitor to compare the target dataset to the baseline dataset over those 6 weeks. In that demo, we printed out the metrics using code and were able to plainly see the drift over time. In this demo, we're going to use visualization tools built into ML Studio to explore those same metrics. Now, to view data drift monitors in ML Studio, we need to use the Datasets feature. So let's go ahead and click on Datasets in the left-hand menu. So this screen shows us all of our datasets. Here we can plainly see our target and baseline datasets. We can also see the dataset we created in an earlier demo. But what we really want to see is the data drift. Now to see that, we need to click on the Dataset Monitors tab at the top of the screen. Now this screen shows us all the data drift monitors that we created, and in our case we've only created the one. And in fact, we can see that we've associated our baseline dataset and our target dataset to this monitor. So let's go ahead and click on it. So now we're seeing all kinds of information about our data drift monitor. Let's start on the top left in the summary section. First, we see the drift magnitude. This metric tells us how far out our target dataset has drifted from the baseline dataset. A value of 0% means that the datasets are identical, while 100% means that the datasets are completely different. In our case, we're seeing a substantial difference indeed. In fact, it's almost completely different. The threshold value tells us when alerts will be triggered. Now, we don't have any alerts, but since our magnitude is greater than our threshold, we definitely would have triggered an alert. Then we have the top drifting features. Here we see that BMI drifted quite substantially while pregnancies and age only drifted a little bit by comparison. Now, since these were the only fields that we're monitoring, they're the only ones that we see here. Now let's look at the Monitor Time Series section. This chart tells us which date ranges the drift data is available for. In our last demo, we ran the exact same datasets in a tight loop, so the result is that the chart is pretty flat, meaning that there was always the same amount of data week after week. In real life, each time period would probably have different amounts of data coming into the system for different time periods. Now let's scroll down and look at the drift magnitude trend. Now in this chart, we're seeing how the drift magnitude changed over time. We can see from the chart that our drift got consistently worse over time. Now let's scroll down to the next chart. In this chart, we can see our drift magnitudes per feature over time. So in this case, we can see that BMI was always the biggest drift, but that it became a major contributor as more weeks passed by. Maybe pregnancies and age were getting worse too, but BMI was so egregious that the impact of the other drifts actually appeared to get smaller. Now let's scroll down to the next piece of analysis. In this table, we can see a breakdown of each of our important features. In the data drift contribution column, we can see that the contribution of BMI to the overall drift is more than an order of magnitude greater than the other features. Now this table is actually a breakdown of the chart that we saw above, so you can change how that chart is presented simply by selecting and unselecting each of these fields. Anyway, let's see another chart. Let's scroll down to the next one. In this chart, we can explore individual features and their drift metrics over time. So in the Select Metrics field, let's choose Mean Value. Now notice that the chart updates to now show the mean value for our BMI over that time range. What we're seeing here is that the mean BMI in our target dataset was changing over time, and that makes sense since we augmented the data that way. In reality, this would be very important. Imagine having an uptick in diabetes over a few years and wondering why that might be. Well, by looking at your data drift, you might be able to find out. In this case, you would see that patient BMI has increased over time, and that might be why we're seeing more diabetes now than before. Finally, let's scroll down to the last chart. In this chart, we're seeing the feature distribution in both our baseline and target datasets. This chart uses the same selections that we set in the previous chart, so that means that this chart is analyzing BMI. The x-axis represents the BMI of patients in the dataset, and the y-axis represents the probability that a patient is that BMI. So let's analyze what this chart is telling us. First, the baseline series is telling us that we have a lot of patients around 20 BMI and another hump around 35 to 40 BMI. Meanwhile, our target series is telling us that we have a lot of patients around the 35 to 40 BMI mark and way more patients at extremely high BMIs. We also have no patients less than 30 BMI. Now, since we created our target dataset by augmenting the baseline dataset, well, this is exactly what we expect to see. Anyway, that's it. That's how you visualize, pivot, and play with the data drift information that you collect with your datasets over time. When it comes to managing, manipulating, or otherwise exploring data, it's of the utmost importance that sensitive information and personal details in that data should be kept private. Imagine a dataset that includes patient data. No one would want that information getting out, right? So, how do we go about doing that? Well, one method of dealing with personal details in data is through obfuscation by aggregation. For example, imagine looking at diabetes data and getting useful information like how many people under 50 have diabetes. You can still determine a lot of information from that data set through aggregation, but you remove a lot of the specifics. But could private information still be gleaned from aggregate data? Well, yes and no. It really depends on your data set. So there's still things that you have to do to prepare your data set. For example, if you had 10 people in your diabetes dataset and 10% of those people had diabetes, then you know that one of those people has diabetes and you may be able to figure out which one through other queries. So let's talk about how we can keep our data private. Now, at the end of the day, privacy of data is the choice of the individual, isn't it? So the best way to keep your data private is simply to opt out of it. Consider using browsers or apps on your phone. Lots of those apps will ask if they can collect certain information about your usage and improve their product. Well, a user can simply say no, and so that means they're opting out of the data collection and their data is now private. Of course, that being said, opting out can affect a user in other ways. So, for example, imagine signing up for health insurance and the insurance company would like information about family history of diabetes. Some companies might let you opt out of that data collection, but then your premiums will be higher. And some companies might not allow you to opt out and choose not to have you as a client at all. Now, what that means is that sometimes participation may actually be more beneficial to you than opting out. In reality, the data collection will occur with or without you. So data about users all over the world will be collected and studies performed nevertheless. So in reality, opting out really only works if everyone opts out. Now, one way to deal with privacy in data is to use what's called differential privacy. And that sounds like a fun term, so what is it? Well, differential privacy is primarily geared towards trying to protect individual pieces of data in your dataset. Now, how does it do that? Well, differential privacy effectively adds noise during the process of analysis. Now, I won't get too deep into the actual math on this. In fact, it's worth knowing that the people working on this are folks from Microsoft, Harvard University, and a bunch of other folks way smarter than me. But the crux of it is that noise is added in such a way that aggregations like sums and averages and counts all remain statistically consistent. So we can actually change the data but not the overall data set itself. Now, what that means is that if you were to look at any of the individual pieces of data in the privatized data set, it would be different from the original, and so there's no way to gain anything useful from it. So individual data is not exposed. Meanwhile, at the aggregate level, the data looks almost exactly the same. It's actually even more impressive than that. The tools that are used to implement differential privacy in your dataset produce a different result with each run. In other words, the noise changes with each analysis. Now again, the aggregate results will stay the same, but the injected noise will be different. Now, from a terminology perspective, what that means is that the differential privacy tools produce non-deterministic results. You can feed in the exact same dataset time and time again, and you will never be able to predict what sort of noise is being injected, how it's being injected, and where it's being injected, or at what magnitude. In reality, even the aggregate results will be slightly different with each run too, but at the aggregate level the differences will be much more subtle than at the individual data point level. But rest assured that each run produces a slightly different result that you can't predict. So just how do you go about adding noise to a dataset, and can you control it? Well, the short answer is yes, you can control the amount of noise injected into your dataset. You can do that through an epsilon parameter that you pass into the differential privacy methods. The epsilon value will dictate how much noise will be applied to your dataset. It's a simple float value. Higher epsilon values will result in the original dataset and the private dataset being much more similar, whereas lower values will add much more obfuscation. The epsilon value is configurable because it helps you to configure your data in a way that minimizes the risk of data exposure. Obviously, you want to completely eliminate any sort of personal information being seen, so you want to set that epsilon value such that you reduce that risk. But at the same time, you don't want to make your data completely useless by adding so much noise that it doesn't resemble the original dataset at all. And that's actually an important thing to understand here. The noise that's injected into the dataset is applied to everyone in the study. The entire dataset will have the noise applied to it. You don't get to pick and choose which individual data points will be augmented, and you don't add dummy data points to the dataset. The existing data points will be adjusted across the entire dataset. This is how the aggregate can remain the same, while individual data points can be made more private. Okay, so there has got to be a catch, right? We can play around with these epsilon values to add more or less privacy, so why don't we just maximize that privacy? Why is this configurable at all? Well, the short answer is in the accuracy of the dataset. As I said, the epsilon value is a simple float number. The lower the value, that is, the closer to zero, the more private the individual data points will be. It means that more noise will be applied to the dataset, but the more noise you inject into the dataset, the less accurate the overall dataset will be. Which means the opposite is true. The higher your epsilon values, the lower your privacy protections. But it means that your dataset will be much more accurate because it will be much more aligned with the original, unaltered dataset. So what this means is that you'll have to be very careful to balance your privacy with your accuracy. How much are you willing to sacrifice accuracy at the individual data point level for the good of privacy? Of course, that begs the question as to just how much the accuracy is actually impacted by privacy. So let's hop into a demo and see that in action, shall we? In this demo, we're going to use the Smart Noise SDK to generate and submit differentially private queries. Differential privacy is a technique used to preserve privacy of data points by adding noise to the data. So in this demo, we're going to show how to use the Smart Noise SDK to create and manage that noise. Alright, so one more time, let's head over to the Azure ML Studio in our browser. Now, in an earlier demo in this course, we cloned a Microsoft sample repo. In this demo, we're going to use one of the examples from that repo. So let's head over there to explore it. Let's click on the Notebooks option in the left-hand menu. Now let's open the MS-Learn DP-100 folder and click on the 13 Explore Differential Privacy file. Now this sample from Microsoft goes into a lot of detail about the Smart Noise SDK and differential privacy in general. I highly recommend you spend the time to read this sample in detail. However, in the interest of time, I'm going to gloss over a lot of the stuff that's in here and just work on the code. So let's get to it. Let's scroll down to that first code snippet. Now in this snippet, we're installing the Smart Noise SDK on the compute instance. Smart Noise is a Python package from OpenDP. And OpenDP is actually a joint project between Microsoft, Harvard University, and a whole bunch of others. It's still a fairly new SDK. Its purpose is to inject and manage noise in your data to help secure your data and keep the real data private through obfuscation. Anyway, let's run this code cell by clicking on the play button to the left of the code, and this will install the SDK package. Now let's scroll down to the next code cell. Now, in this code cell, we're going to load some data. Specifically, we're loading a CSV file that contains diabetes patient data into a pandas data frame. We'll then output some information about the data to the screen. So let's go ahead and run this code. Now we can see from the output that we have 10,000 patients that each have a number of features, like pregnancies, blood pressure, age, BMI, and so on. And for each of the features, we have various statistical analysis about them, like min, max, mean, and so on. So we have our dataset. So let's scroll down to the next code cell. In this code cell, we're going to use Smart Noise for the first time. Let's look at this code and see what it's doing. On line 7, we're creating a Smart Noise Analysis object. On line 9, we're loading the diabetes dataset. And on line 12, we're specifically grabbing the age column. Then on line 15, we're using the smart noise analysis object to inject a whole bunch of noise into our data. On line 16, we're defining how much noise we want. The value is always above 0, with the lower values meaning greater privacy, while higher values are closer to the original dataset. On line 17 and 18, we define the min and max ranges for our augmented data. On line 4, we had set the min and max ages to 0 and 120 years old. On line 25, we output the mean of our noise-injected data, and on line 28, we output the mean of our original dataset. So let's run this code and see what we get. So remember that we injected a whole bunch of noise into the dataset, yet our mean values are virtually identical. Now, how do we know that we really did anything? Well, let me show you. Let's scroll down to the next code cell. In this code cell, we're exploring our original dataset by laying out the actual ages in a histogram so you can see what the actual distribution of ages is. Let's run this code cell and look at the chart it produces. So you can see the majority of our patients are between 20 and 30. The next hump is between 30 and 50, and then the ages drop from there. Now let's scroll down to the next code cell. In this code cell, we're once again using the smart noise analysis object. This time we're creating a histogram output with injected noise. Now once again, we're using a 0.5 epsilon and an age range of 0 to 120. The results are then put into a histogram chart with the original dataset put alongside it. Let's run this code cell and see what we get. Now, here we're seeing that the two datasets are virtually identical in terms of the counts. So what is this telling us? Well, it's telling us that while we injected noise into the data, we didn't affect the overall statistical structure. The data is different, it has noise in it, but the total number of values that we found in each bucket is the same as it was before. Now, let's scroll down to the next code cell. Another goal of data analysis is to create relationships between data, and smart noise can provide a differentially private covariance function for this reason. In this code block, we use the smart noise analysis object to create a private covariance between the age and blood pressure features. So let's run this code to see what I mean. Notice that both the outputs are positive. There are certainly different values, but statistically the data should not be changed that much. In both cases, the positive result is what's important. The positive results suggest that older patients, the left side of the covariance calculation, have higher blood pressure, the right side of the covariance calculation. If the number was negative, it would suggest that younger people have higher blood pressure. Now, smart noise also includes a mechanism to perform SQL-type queries against your data to retrieve differentially private data too. So let's scroll down to the next code cell. Now, in this code cell, we're importing a YAML file into a collection metadata object. This object defines the data in our dataset. Let's run this code block to see what I mean. So you can see in the output that our metadata object has now defined our diabetes dataset. The data types and ranges for each feature in our dataset is now understood. Now let's scroll down to the next code cell. In this code cell, we're loading in some readers. In order to run SQL queries, you need a reader. On line 3, we create a pandas reader that imports our original diabetes data and our metadata definition. On line 4, we create a private reader object that imports the same pandas reader and the metadata definition again. Let's run this code and configure our readers. Now let's scroll down to the next code cell. So now we're actually going to execute some SQL queries. On line 1, we define the query. This query is asking for the average age of all the patients in the dataset grouped by whether or not they're diabetic. On line 3, we execute that query. So let's run this code and see what we get. So what we're seeing is that the average age of people that are not diabetic is around 27 years old, while the average age of the people that are diabetic is around 36. Now notice that we executed that code against the private reader, and remember that the point of privacy is to add noise to the data. So let's scroll down to the next code cell. In this code cell, we're executing the exact same query, but this time against a pandas reader. and that means that we're not injecting any noise into the data. So let's execute this code now. So now we can see that our data is very similar, which is exactly what we want, but it's not the same. We want the privacy, but we don't want to affect the data integrity. So let's scroll down to the next and last code cell. Now in this code cell, we're playing with the epsilon value in the readers. Remember that we said a higher epsilon means less privacy because the data will be very similar to the original. Now notice that on line 1, we create a private reader with a very high epsilon, while on line 6, we create a private reader with a very small epsilon. Now let's run this code snippet, but let's make sure to keep our real numbers visible from the previous code cell. Now notice that our reader that used the higher epsilon is much closer to our original dataset. Meanwhile, our reader that used a smaller epsilon is further away from reality. That's the game. The lower the epsilon, the more privacy and noise you introduce, but the less accuracy you have. So at this point, we created a dataset and used the Smart Noise SDK to create noise on the age feature in our dataset. We were able to see how that didn't adversely affect the distribution of data. There was an impact on covariance, but the end takeaway remained correct. We then used readers to execute queries against our private data. And lastly, we played with the epsilon values to show the impact of additional noise on the accuracy of the data. So in this course, we've examined machine learning model monitoring. And we did this by exploring how application insights can be used in Azure Machine Learning Web Services, monitoring models and creating a data drift monitor, creating and monitoring data drift using Jupyter Notebook and Python, and differential privacy with Python. In our next course, we'll move on to examine Azure Monitor Service.